Bienvenue à ce petit déjeuner avec des têtes et papineaux. Welcome to Bacon and Eggheads. I am Natalie Goto, Chair of the Bacon and Eggheads Committee and your host for today. Pour suivre notre événement français, veuillez utiliser le bouton de traduction simultanée en bas de votre écran. To hear the English interpretation during a brief French video of today's presentation, please choose the English language channel. Today, we have the pleasure of hosting a leader in the field of carbon capture, utilization, and storage, Dr. Lawton. But first, let us honor the Indigenous peoples of all the lands we're on today. Even though we are meeting on a virtual platform, we acknowledge the importance of the land which we each call home. From coast to coast to coast, we acknowledge the ancestral territory of all the Inuit, Métis, and First Nations peoples. We commit to improving relationships between their nations and ours, and pay respect to the traditional knowledge keepers and their courageous leaders. Today's talk will provide us with a cutting-edge view of all the technologies that will help Canada achieve a sustainable, carbon-neutral future, a topic that concerns all of the 50,000 researchers that are represented by the Partnership Group for Science and Engineering. The Partnership Group is a registered, not-for-profit umbrella organization of 21 science and engineering societies, including the Canadian Federation of Earth Sciences, who kindly nominated Dr. Lawton for today's event. We encourage all audience members, and especially the parliamentarians who are joining us today, to submit questions at any time during or after the talk by clicking on the Q&A button at the bottom of the Zoom screen. Before we start, we would like to thank our sponsors who are listed in the opening slides. We are grateful to all of them and to the speakers of the House and the Senate who have supported this series for more than 2 decades. It is my great pleasure to now invite Dr. Alejandro Adem to introduce our speaker, Professor Lawton. Dr. Adem is the president of NSERC, an organization that's been a strong long-term supporter of the Bacon and Eggheads series. Over to you, Dr. Adem.
Thank you. Thank you very much. Bonjour à tous et à toutes. Good afternoon, everyone. Le CRSNG est partenaire des petits déjeuners avec des têtes à papineaux depuis de nombreuses années, et je suis heureuse de le représenter ici aujourd'hui. When I last addressed the Bacon and Eggheads audience this past December, I commented on how we, as Canadians, were living with changes and challenges. J'avais examiné la vérité de cette constatation et sa pertinence par le passé, dans les années précédant la pandémie de COVID-19. Today, even as we still struggle with this terrible pandemic, I want to take our focus to the changes and challenges of the future. The world we will live in after COVID, hopefully, is gone. In particular, I want to raise the topic of climate change. At the Leaders' Climate Summit that US President Biden convened on Earth Day last month, our Prime Minister, Mr. Trudeau, announced that Canada would reduce greenhouse gas emissions by 40 to 45% below 2005 levels by 2030. How are we going to accomplish that? It really is a scientific, technological, and societal challenge. Le changement climatique est également un thème important du dernier budget déposé par le gouvernement du Canada. Le budget désigne la technologie de captage, d'utilisation et de stockage du carbone comme étant un outil important pour réduire les émissions dans les secteurs aux émissions les plus importantes. Canada is a leader in this field with domestic projects that currently capture 4 megatons of carbon every year. Looking ahead, we have the technical and geological capacity to capture and store much more. Quel est le rôle du CRSNG dans ce contexte? Le CRSNG est le seul organisme public qui investit des sommes importantes à la fois dans la recherche axée sur les découvertes et dans l'innovation orientée par le marché. Nous faisons le lien entre le milieu postsecondaire et l'industrie. For 2019-20, the last year for which we have the breakout data, we estimate that we invested about $150 million in climate change and clean technology research. It's a lot, but clearly not enough. That's a 22% increase over the past 10 years. For CO2 capture and storage alone, the investment was over $5 million, up 130% over 8 years. Again, it sounds like a lot, but I think we have to do a lot more. As I mentioned a moment ago, CO2 capture holds great promise for Canada. Le conférencier d'aujourd'hui est bien placé pour nous parler des derniers travaux de recherche dans ce domaine. Dr Lawton est l'un des directeurs à Carbon Management Canada et professeur émérite de géophysique à l'University of Calgary. And if I may say so, I visited Calgary many times myself as a scientist, and it's always been a very enjoyable visit, and in particular with folks in the geophysics, exploration geophysics community. So welcome, Professor Lawton. Il est le lauréat de nombreux prix, notamment d'un prix Synergie pour l'innovation décerné par le CRSNG. Please join me in welcoming Professor Dr Lawton. Merci beaucoup.
Thank you, Dr. Adam, for your very kind introduction. I also wish to thank the Partnership Group for Science and Engineering for the invitation to make this presentation today. I will now share my screen, and before I start the presentation, I'd like to make a territorial acknowledgement. Just would like confirmation that my slides are visible.
Looks great.
So I'd like to take this opportunity to acknowledge the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy comprising the Siksika, Piikani, and Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to the Métis Nation of Alberta, Region 3. As Dr. Adem said, one of the biggest challenges or threats that we face today is rising global temperatures caused by increasing levels of greenhouse gases in the atmosphere, particularly CO2. And this increase is linked mainly to the combustion of fossil fuels. Canada, along with many other nations, is committed to a net zero carbon economy by 2050. And we have a new target of a reduction in emissions between 40 and 45% below 2005 levels by 2030. Now, this is a huge challenge. And today, I'm going to talk about one mitigation technology or cluster of technologies known as carbon capture, utilization, and storage, or CCUS for short, and why this is so important for Canada, and describe exactly what this technology does for us. So what is carbon capture, utilization, and storage? If we think of carbon capture, we should think of carbon as being CO2. It's really a method to concentrate CO2 and then be able to do something with that CO2 that we have captured. So there are various ways of dealing with the CO2. Two are utilization and conversion, which have some sort of an overlap, which I'll describe, but that's where we take the CO2 and either make useful products or use it for useful purposes. Today, I'll focus a little more on carbon storage, commonly known as CCS, and the progress that we're undertaking in Canada and the possibilities for the future. I'll describe some of my own research at the CMC University of Calgary Field Research Station in southern Alberta, and then reflect upon some of the opportunities and barriers for implementing this technology at scale towards this goal of a net zero carbon economy. So here's the challenge that we face, as Dr. Adem well posed. We're dealing with significant increases in this concentration of carbon dioxide in the atmosphere. If we look here in the last 200 years, the levels of CO2 have almost doubled, so we're now over 400 ppm or 0.04%. So this is attributed to combustion of fossil fuels, increasing the CO2 concentration in the atmosphere. And if you look at Canada's greenhouse gas emissions, our total emissions in 2019 were around 730 megatons of CO2 equivalent. And of that, this pie chart below shows the various gases that contribute to these emissions. And what we're going to be focusing on today are the CO2 emissions, and we're just under 600 megatons of CO2 per year. The other gases are mostly methane and these other gases shown here. So our challenge is to reduce those emissions by a variety of technologies, including carbon capture and storage. So on the capture side, as I mentioned, it's really the separation of CO2 from other gases. And the traditional view of carbon capture is from large point source emitters like power stations or industrial facilities, which have smokestacks, which emit exhaust gases or what are known as flue gases into the atmosphere. So we've developed technologies to prevent that CO2 from going into the atmosphere. And I won't be talking specifically about the capture technology, but there's a range of them that are quite well established for extracting CO2 from these exhaust gases. More recently, there's been interest in development of the ability to capture CO2 directly out of the air or out of the atmosphere. And this is known as direct air capture. And this is difficult because the concentration of CO2 in air is small, it's 0.04%, but this photograph is courtesy of Carbon Engineering from Squamish, BC, where air is sucked through this fan here into this purple colored building, and through a chemical process, the CO2 is captured. Now, once we have captured that CO2, what can we do with it? So we'll look at three different possibilities here: utilization, conversion, and storage. And I mentioned there's this a gray zone between utilization and conversion. If we look at the utilization first, then currently the largest utilization of CO2 is actually in enhanced oil recovery, where CO2 is injected into the subsurface to oil reservoirs, and more oil is produced through that CO2. Now, this might sound counterintuitive because we're trying to reduce the use of fossil fuels and prevent the atmospheric release of CO2. However, the energy transition is going to take a long time, decades. So in the meantime, we'll be using fossil fuels. So let's find a way to use them with the least amount of emissions. And with enhanced oil recovery, every time we are injecting CO2 into the subsurface for EOR, as it's known, we are actually storing a lot of the CO2. Another more recent uptake in terms of utilization or also conversion is cement or concrete. And there's a Canadian company, Carbon Cure, that recently was a co-winner of the Carbon X Prize for advances in being able to include CO2 mineralization into concrete. So this has scalable potential into the future. And then other types of utilization we're more familiar with, for example, large greenhouses shown here, which we use for improving the productivity of greenhouse production. On the conversion side, if we look at the products on the right here, so this is a list of outputs from various industrial processes. If we look at being able to then use CO2 as a feedstock, provided we work on it with we drive that with renewable energy through some sort of industrial process, such as an electrolyzer, for which we would need, say, water, then we can manufacture from a raw feedstock of CO2 a whole range of different products: carbon black, carbon nanotubes, carbon fiber for the built environment, plastics and polymers, pharmaceuticals, and in particular, green fuels and green hydrogen, which are quite scalable in terms of what we can look at into the future, all using renewable energy to drive the extraction of the conversion of CO2 to useful outputs. However, today I'm going to talk about now what we mean by CO2 storage or carbon storage. And this is where if we look at these slides from the top left, what we are traditionally doing is what's called carbon storage in sedimentary basins, where we inject CO2 deep underground. I'll describe that as we go forward. And then more recently, there's been other ways of storing CO2, which I'll describe later: mine tailings and basaltic rocks. And there's also agricultural ways of storing carbon with agriculture, with soils, with afforestation, and biosolids. Today, I'm going to be focusing on the geological side. I won't have time to cover these agricultural and other topics. So I've used my network across Canada to provide many of the slides, and you'll see the acknowledgements below each of the pictures, and I'll describe some of these as we go through. So the question is, how much CO2 can we store? And if we think of that in terms of the goal, we currently emit 600 megatons of CO2 per year. So over the next few slides, I'll be using the term CCS occasionally. So that's an acronym essentially for carbon capture and storage, or just think of it as CO2 storage. And what's interesting is that CO2 is a really interesting fluid. So this is what's called a phase diagram, which on the x-axis here, we plot temperature, and on the y-axis, we plot pressure. So at room temperature, say 20 degrees Celsius and 1 atmosphere pressure, which is 0.1 megapascal, CO2 is a gas. But as we inject, if we go underground, then the temperature increases at about 25 degrees per kilometer of depth. And also, for the temperature, the pressure increases as we go deeper underground, and we'll enter this region known as the supercritical state, where CO2 acts a bit like a liquid and also a bit like a gas. So all of the major carbon storage projects are really using CO2 in the supercritical state, because it is the most efficient way to store CO2 underground. So let's tunnel in and look at the rock itself. So a sedimentary rock, whether this be a sandstone or a silt, you've probably seen those in outcrops. What we have is a grain of rock, or multiple grains that are in contact, and what we've shown in blue are what are called the holes or the pore spaces in the rocks. And typically these are filled, in the case of an oil field, these would have oil in them, or in the case of what we call a saline aquifer, they'll be filled with water. So we can store CO2 in either depleted oil and gas reservoirs, or we can store it in these saltwater units, or saltwater aquifers as they're called, because that water is not really useful to us. So if we inject CO2 into it, then the CO2 will occupy these pore spaces in the salty water, and it'll remain there. It'll dissolve into the water. It'll stick to the grains of rocks. And that's how we get the storage of CO2 in these types of rocks. So how do we know where these rock layers are below us? So we use technology, which I'll describe in a minute, but let's just look at this picture. This shows an outcrop of layers of different types of rocks. You can see here it's horizontal, different layers. So what we look for are certain layers of rocks that have properties that are very useful for storing CO2. So in this cartoon on the right, we've identified our storage interval here, and we look for rocks that have what are called high porosity, or have a large proportion of holes. More than, say, 20% of the rock is these holes. And another phenomenon or property known as permeability, so that if we push fluids into these rocks, they will flow through easily and be able to move through the rock matrix itself. But because these interesting properties of CO2 is that it's a liquid, but it's also a bit like a gas, it'll be a little buoyant, so it'll want to move upwards. So what we have to do is find an overlying layer that's part of what we call a storage complex, which is a seal. So it says very small holes or tiny holes, less than 0.1%, and very low permeability. So fluids will not flow upwards through these seals. So that's the type of structure that we're looking for in the subsurface. And how we get there is we use technology used by the oil and gas industry known as seismic imaging. And this is, think of it in medical situations. We use ultrasound to image inside of our bodies. In exactly the same way, we use a larger form of ultrasound to look inside the earth, known as seismic imaging. So on the left side here, we have what's called a seismic section. So consider this as a slice through the earth. So it's distance along the top, and then this is depth. And all these different colored bands are really representative of what we can picture below the surface. So we use that to find out where these various different layers are, and then we can drill a well and find out the properties between these different units. So we can do this in 2 dimensions, or we can also do it in 3 dimensions. So you can see here's a cube of rock, and we've cut it away so you can see all the different layering at depths below us, from anywhere up to 4 to 5 kilometers below. So very detailed pictures of the subsurface. So the storage opportunities in Canada. So I'm just going to do a little tour across the country and look at where the storage locations are for CO2. So here in Western Canada, we're very fortunate. The Western Canadian Sedimentary Basin has excellent storage opportunities. So what I've shown here is just this a pattern of little squares coloring from yellow through to red. And this legend here tells us how many megatons or millions of tons of CO2 could be stored within each of the little squares on this map. And this is being work that has been ongoing by a number of groups over the years, and we're starting to now refine that to look at specific locations. But if we add up all that storage capacity, we're somewhere around 400 gigatons of capacity, which is enough to store all of Canada's emissions for close to 1,000 years. So very great opportunities. So there's a number of projects that have started already. This example by the so-called Quest project in Alberta, where CO2 is being stored by Shell and its partners. Here's just a schematic of the Quest project. CO2 is being stored at a depth of 2 kilometers, so it's in the supercritical state. And the rocks down here are very suitable for storage. The best unit is this known as the basal Cambrian sand. It's a very porous, high permeability sand, and it's overlain by thick layers of salt. So if you've ever been on a farm and seen a salt block that cows lick, you see it's very solid, and there'll be no way that CO2 can move upwards through those salt layers. So this project has been running since about 2015, and as of December 2020, there's been more than 5.7 million tons of CO2 stored in the Quest project. And that's many hundreds of thousands of cars taken off of the road in terms of equivalent emissions. Also in Alberta, recently is the Alberta Carbon Trunk Line that has been completed. It's a 150-kilometer pipeline from Edmonton down to towards Red Deer, and it shows the full technical cycle here from capture, transportation, utilization, and storage. The pipeline capacity is 14 million tons per year, and currently it's being used by Enhanced Energy for carbon dioxide enhanced oil recovery project in an oil field near Red Deer. And already, just to recharge the reservoir or rebuild the pressure, there's been 1 million tons of CO2 stored since the beginning of the year. If we move into Saskatchewan, there's a very successful project known as Aquastore Boundary Dam, and this is CO2 capture from a coal-fired power station. And part of that CO2 stream that is captured is being injected in a project known as Aquastore. And this is actually the deepest well in Saskatchewan. It's 3 kilometers deep, and the CO2 is being injected into a layer down near the base of this picture that you see. And so far, there's just this, in 1 year, 370,000 tons of CO2 has been stored. And these pictures below, I mentioned seismic imaging for being able to look at where we can store CO2, but these are images of doing these seismic surveys again over a period of time and being able to see where the CO2 is in that horizon that we're injecting it into. So here's early on, you can see the yellow area here is where the CO2 is viewed. So here's the scale up to 1,000 meters at the bottom. And then a year later, here's a bigger yellow patch here and bigger still on the third. So these being able to actually see from the surface, looking down from up here, we can actually see where the CO2 is that we're injecting, even at this depth of 3 kilometers. We can move across the country, storage opportunities in Quebec, mostly in the St. Lawrence Valley, St. Lawrence lowlands. There are a lot of large emitters east of Montreal, and work being done by my colleagues at Laval and INRS has mapped the potential for the St. Lawrence lowlands, and somewhere between 3 and 8 gigatons could be stored in this region. We now go to Eastern Canada. Colleague Grant Walk from Dalhousie provided me this map that looks at the storage potential around Nova Scotia. It's shown here, and they identified the point source emitters through these provinces, and this is a pipeline that goes into the offshore Sable Island. So this ultimately could be repurposed as a CO2 pipeline, and the circles represent radii of 150 kilometers away from each of the point emitters, which is probably the maximum pipeline distance we'd want to consider, but there are large storage opportunities, most likely in the offshore. So that work is now currently being developed and storage capacity being estimated. So one critical element of these CO2 storage projects is monitoring and verification. This is the area that my own research works in. And this is really an answer to public questions about carbon capture and storage, such as, will CO2 leak back into the atmosphere? Is it safe? Are there environmental concerns associated with it now or in the future? Will it stay underground? Will it move up and contaminate shallow aquifers? Will it cause earthquakes and reactivate faults? And how much does it cost? So let me say that CO2 is a very safe technology, CO2 storage, because we design the projects to be secure and we monitor to ensure that they're behaving as expected. So to answer these questions, this would be no, it will stay underground, it will not move up, because we monitor it, and if there are issues that develop in the projects, we can intervene and mitigate those issues. Will not cause large earthquakes because we only inject CO2 at a really fairly modest pressure. And it's not like you've heard about with hydraulic fracturing. And we can discuss more about that perhaps in the Q&A. And I'll talk about the cost a little bit later on as well. So our research, we have a facility in southern Alberta known as the U of Calgary CMC Field Research Station. It's a research site for the development and validation of technologies to verify that the CO2 is staying where we think it is. So let's revisit that medical analogy. You know, we all go to the doctor once a year for a checkup to ensure that our body is functioning as it should. And we shouldn't wait if we don't visit the doctor, we shouldn't wait till something goes wrong before we go to the doctor. So this monitoring is exactly the same for these types of projects. We monitor continuously what is happening below the surface to ensure that it's behaving as expected. And some of the technologies that we're using at the site are optical fiber based. So this is an amazing technology that we can, with these thin optical fibers, we can measure temperature, we can measure pressure underground. So we're essentially measuring the heartbeat of this facility as it's operational. And to quickly describe what our site looks like, we have a tour by one of our staff members, Maria McKay. I'll run a video.
In collaboration with the University of Calgary, we have developed a research site that is state-of-the-art in southern Alberta. Innovators and industries from the whole world come to work here to test and develop technologies that will allow us to monitor and manage CO2 or methane when they move in the soil or in the air. Hello, everyone. My name is Marie Mackay, a geophysicist working in CMC at the field research station. Here we inject a small volume of CO2 at a small depth. For now, we have 300 tons at 30 meters depth. The goal is to develop technologies to monitor that CO2. What are the most effective technologies, or what combination of technologies would be more efficient to detect that small volume of CO2 at a low depth?
Yes, so Maria is one of our staff members doing a great job on working with some of the monitoring technologies at our site. So again, we're being able to essentially continuously monitor this. So imagine walking around where you continuously monitor your own blood pressure and temperature. This is what we're doing in the subsurface. So in the storage area, there are some new developing technologies. And one of them is CO2 storage, or known as mineralization in mine tailings. And colleague Greg Dipple from UBC provided the slide that is really showing what happens where we have a CO2 supply whether this be from a point source of CO2 or even directly from the air. That CO2, this is a natural process. It'll react with the minerals. These are magnesium silicate type materials known as ultramafic or ultrabasic rocks. And this precipitates in the mine waste to form mineral carbonates, particularly calcium carbonate, magnesium carbonate, and that's permanent storage. So if we look across Canada, it's a potential for mineralization and mine tailings. It is large. So on the left here, we have a map of Canada, and these purple dotted lines really separate, if you like, the sedimentary basins that we talked about in terms of conventional storage from areas where there are minerals that are could be mined with tailings that could be used to absorb CO2. And what's interesting, if we think of the energy transition, we're going to see a big upturn in the need for metals like copper, elements like lithium, cobalt, and these are contained in these mineralized belts throughout Canada. So the storage potential, if these mines get developed, are large, and these are just some of the numbers shown in here. Mineralization capacity in gigatons for the various provinces. And if you sum it up, close to over 200 gigatons of CO2 could be stored as mines get developed and the mine tailings are used to absorb CO2 and store it permanently. Thanks to Greg Dipple here. Now, another interesting project that is just getting started is actually offshore the West Coast, known as solid carbon. And this is a project being pioneered by Ocean Networks Canada and the University of Victoria. And it's using basaltic rocks. The picture shown here is basalt. And the picture at the bottom here is the seafloor, or picture a map offshore Vancouver Island, where the oceanic floor rocks are all these basalts. And this area known in here is really a suitable location, a great location for demonstrating this opportunity to capture CO2 directly from air, using renewable energy to actually do that capture, and have a marine platform sitting out here which would inject CO2 into these basalts, and then have a monitoring scheme out at sea to ensure that it stays where we think it is. And this is, again, a permanent solution ultimately, because the CO2 will mineralize into carbonates in the basalts. So this is a project with probably a longer time scale to get going, but it's really another opportunity. So let's move into a little bit of a discussion about what we've been covering here. One of the topics that came up in the questions, what are the costs? And they're very varied, because every project will be a little different. So this is the type of range that we will see: $30 to $80 per ton captured from power plants. Direct air capture, also known as carbon dioxide removal, somewhere between $100 to $300 per ton. And you see that the capture costs are really the high part. The transportation and storage costs are really quite low in terms of the scheme of things. And the total cost somewhere between $40 and $100 per ton, or impact around 20 to 30 megawatt hours in terms of the cost of this additional technologies to capture the CO2. So in terms of what this cost is, we have to compare this against the cost of doing nothing. And a good barometer for that measure is the insurance industry. And there's been recent reports that over the last decade, about $1.8 billion have been spent on or caused by natural issues due to insurance losses attributable to climate change. So we have to balance those concepts. So if we look at the path forward to a net zero economy, this graph is really tailored for Canada. It shows our CO2 emissions here on the y-axis, and just this is the CO2 part. It's not the total greenhouse gas emissions. It follows the red line. And over the past 15 years, it's been relatively stable because of improved efficiency in both industry and activities. And if we looked at business as usual, it would follow this line around 580 to 600 megatons per year. But in order to reach the 2030 goals of 40 to 45% below the 2005 levels, we need to follow this trajectory. And then towards a net zero economy, in 2050, it would have to be way down here. There are always going to be unavoidable emissions. So we have to balance that against technologies known as negative emissions, which I'll talk about in a little while. So the mitigation measures represent what can we do in here, and what is the role that CCUS can play in this mitigation process. And if we use what are called the wedge diagrams published by the International Energy Agency and other groups, these are the types of contributions to these wedges that we see. When CCUS here, shown in this yellowish color, will contribute probably around 15 to 16% of the total mitigation. The rest comes from renewables, expanding renewables, bioenergy, hydrogen, which actually itself will generate some CO2, advanced electrification. So these are all of the different wedges that we will require in order to get to net zero carbon, combined with negative emissions. So that's a tall order, because that'll mean we'll need several dozen Quest-sized projects and other types of utilization to achieve these goals. So if we look at those three options, and again, there's no single technology that is going to get us there. We need all of these in order to meet the goals that we've discussed. So on the utilization side, we're currently relatively low on the x-axis here. It's really the technology readiness level for the technologies to enable us to get to large-scale emissions reductions by 2030. So for utilization, this is the current status. The potential will increase primarily due to probably the cement industry development, which we're seeing. But the existing technologies for utilization, and close to 80% of all utilization is currently in enhanced oil recovery. And we can increase that probably to a mid-scale-up potential level over the next 5 to 10 years. CO2 conversion, this is all relatively new technology. Again, that's using CO2 as a feedstock and with renewable energy to drive the process. So that takes a while to get established. So that's why it sits down in the low readiness level, but it has increasing potential, probably due to mostly the development of green fuels. The other utilization or conversion products really depend on what is the market pull for those products. So an overprint on all this is the techno-economic analysis. Whereas CO2 storage, it's well established, a range from really low to high technology readiness levels, as I indicated in the previous slides, but it has very large potential based on what we've been studying so far. However, there's a lot of work that needs to be done in order to get to this level of high scale up by 2030. Companies are very good at being able to do individual projects, but if you're looking at doing dozens of these projects, we need to understand basin-wide issues about what's happening in the different saline aquifers or in the different depleted reservoirs. So there's a strong research component required in all three of these vectors. In addition to the actual technology itself, we need to engage the public to assure the public that this is a way that we can approach emission mitigation strategies. And 10 years ago, back in 2011, I was part of a workshop with the University of Calgary, where we had a public audience, or invited to come, who knew nothing about CCUS, or carbon capture and storage. And we presented the technology. This is actually me at the podium here back in 2011. And we did a poll before at the beginning of the workshop, and we did another poll afterwards. And there was a marked increase in the level of comfort in the public about the technology after people were educated about what it means. And even more recently, a study by the University of Ottawa and courtesy of Patricia Larkin, again, looking at this issue of public confidence and decision-making and how important it is to really engage the public on the technologies and the regulators about how this is so safe. And we're now seeing in the professional community as well on knowledge sharing. So these are just a few examples of of conferences and workshops that are happening even this year. So you see the word CCUS or net zero emissions. All of the major technical societies are really looking at CCUS and how it can be developed in their own disciplines. And in fact, there's a workshop going on in Calgary today, 13th of May, on CCUS in Canada, opportunities for a net zero future. So at the professional level, we're really studying this. We now just need to include the public in the opportunities for implementing this at scale. So let me draw some conclusions here. Clearly, CCUS at large scale is necessary to meet the greenhouse gas emissions goals of Canada. And going further to reach net zero, it'll be virtually impossible without CCUS. And it has to include what I described as negative emissions, which is carbon removal from the atmosphere or direct air capture. So if you combine those technologies with carbon storage, that's a negative emission, and we need that to get to net zero. In order for industry to uptake this technology, we need policy incentives. And I think we're seeing that in the federal budget that was released this year, and likely tax incentives for 2022. And the industry wants regulatory certainty. Before they invest in a technology, they want to ensure that the policy and regulations will continue to evolve to make those projects cost effective. As I mentioned, we need public confidence and to position that CCUS as an economic opportunity. It'll create jobs, services, investment, rather than being viewed as a local cost burden. So let's put this into perspective. If we develop carbon storage in Canada, which we're well posed to do, at the scale necessary to meet our objectives, the size of that industry in terms of the jobs and services would be equivalent to the current level of the industry for producing natural gas. So it's a huge opportunity for us to do. Canada itself is very well positioned in terms of the research innovation for the utilization. Many of the labs all across the country are really active in this area. And on the storage side, as has been mentioned, Canada really has excellent geology, and we have this highly trained workforce of geophysicists, geologists, and engineers to implement CCS at scale. These technologists, we're used to removing fluids out of the ground for petroleum, but we use exactly the same technologies to store it, to store CO2 underground. So we're ready to go. So this is a great opportunity for Canada. And even the new technologies, we hear today a lot about hydrogen. We have what's called low carbon green hydrogen from electrolyzers using renewable energy, but we also have an opportunity to create hydrogen from natural gas as a feedstock, but that requires itself a CO2 strategy. So that is being evolved currently as a part of the new net zero economy. So with that, I'd like to thank numbers of people, certainly the Canadian Federation of Earth Sciences for nominating me for this project or this presentation, and again, the partnership group for making the invitation. And the work that we do at our own field site is really developed, so I acknowledge the support from our team at Carbon Management Canada, the University of Calgary, funded through the Global Research Initiative from the Canada First Research Excellence Fund, and we have industry sponsors as well, all of whom are contributing to this methodology for monitoring secure storage of CO2. So that brings me to the end of my presentation.
Thanks, Maria. So at this point, it's our great pleasure to invite the Honorable Alexandra Mendez, Assistant Deputy Speaker and Deputy Chair of Committees of the Whole, to offer our thanks to Dr. Lawton.
Good afternoon, everyone, and thank you so very much, Dr. Lawton, for this phenomenal presentation. I learned a lot, took a lot of notes. I actually filled out more than 3 pages of notes, and I think I'll bring them back to those who should be interested by these questions. I thank you for a very clear, very succinct presentation. Un très grand merci de la part aussi de mes collègues.
A very big thank you also from my French-speaking colleagues for taking part in this
opportunity to learn more and more about science in Canada at all its applications and all that that we benefit from the scientific minds in this country. It's been a wonderful discovery for me personally, and I think for all of my colleagues. Thank you.
Thank you very much.
Thank you, Senator Mendez. So,
MP.
oh, I'm sorry. Merci d'être venu. Thank you all for coming.
Thank you for being here.
The Bacon and Eggheads events will feature a panel discussion on the dramatic changes in biodiversity that are happening in our own backyards. 3 luminaries of biodiversity research, namely Lenore Farrig, professor at Carleton University, Professor Andrew Gonzalez from McGill University, and Mark Velland, professor from Université de Sherbrooke. This dynamic panel of natural scientists will discuss what is coming to be known as the 6th Great Mass Extinction and its effects on our local environments. As Zoom closes, please take a moment to fill out the short survey that will appear in your browser. To find out more about our events, you can follow at Ottawa Eggheads in Twitter or connect to the Partnership Group for Science and Engineering in LinkedIn. Thanks to everyone for joining us. Merci d'avoir participé à cet événement
Thanks
grandiose.
to you for taking part in this workshop.